So today we're diving into something called the orbital pivot. It's this uh, massive fundamental refactoring that's happening, what, 400 kilometers straight up?
Yeah, a total overhaul, a complete architectural shift.
And our mission really is to get to the bottom of why the old way of doing things in space, this so-called legacy stack, is now, well, basically considered technically bankrupt.
And how it's being completely ripped out and replaced.
Okay, so let's start there. What was this old system?
Well, if you look at the old system, it was so static. I mean, just really inefficient. It was all built on this idea of a bent pipe.
The bent pipe. What does that mean in practice?
It means for decades, you'd launch, a billion-dollar sensor, and all it really did, its main function, was to act like a very, very sophisticated mirror.
Yeah, mirror.
It just captures data and reflects the raw, unprocessed,
Yeah.
just the binaries, straight back down to Earth.
So wait, you're telling me we launched the most complex equipment humanity could build, only for it to act like a $1 billion FTP server?
That's a perfect way to put it. Yes, with just crippling latency.
I mean, you're literally drowning in data, right?
Yeah.
Caching the entire haystack on the ground just to find that one tiny needle of insight.
Exactly. Which kind of begs the question, if the bottleneck isn't the downlink anymore, but where the computer is, how do you fix that?
Okay, so if the processing location is the whole problem, what's the big architectural change that moves the intelligence up to where the data is born?
The industry's answer is what they're calling orbital edge computing. It's a huge philosophical shift.
From what to what?
From thinking of space as a relay to seeing space as a server. The core idea is simple. You just process the data right there in orbit.
Okay, give me a concrete example. What does that actually change operationally?
So instead of sending down a massive, say, 5 gigabyte high-resolution TIFF image of the Pacific Ocean.
And then you have to sift through on the ground.
Right. Instead of all that, the satellite itself analyzes the image. And if it finds an illegal fishing vessel, what it sends back is just this tiny JSON blob.
So just the critical data.
Yeah. The object ID, the coordinates, the confidence score. That little piece of derived truth is the final product now.
But moving all that compute to space, I mean, historically that sounds prohibitively expensive. So that brings up the big question. Why is this possible now?
So this whole refactor, it needed a root user to change permissions on orbit itself. And that's what the sources call the Musk commit.
Ah, SpaceX.
Right. The work with Falcon and Starlink just crashed the cost of launching mass into low Earth orbit. And when that happened, it also crashed the cost of failure.
Which means engineers are no longer locked into building these super expensive, custom, radiation-hardened parts that have to last for decades.
Precisely. If a, $10,000 satellite using an off-the-shelf automotive chip fails, the fix isn't a crisis anymore. It's just relaunched next week.
That economic freedom must have just unlocked an entirely new hardware stack.
It did. One focused on performance, not just, bespoke ruggedization.
So what kind of hardware are we actually talking about here? What's the silicon doing the work?
The workhorse is often commercial stuff, like an NVIDIA Jetson. These things give you massive inference power. We're talking 100 TOPS, tera operations per second, in a tiny power envelope.
And the big win there is you can do CI/CD.
Yeah.
In orbit.
Yes. You can literally push a mission update. You're turning a static piece of hardware into this constantly evolving resource. And then you have specialists like Google's Trillium or Coral.
The Project Suncatcher stuff.
Exactly. That's silicon stripped down for pure inference. And that's how you get real-time flood detection in, like seconds, instead of waiting for the next orbital pass to downlink raw data.
Okay, but building a data center 400 kilometers up. Come on, there have to be huge challenges.
Yeah.
What about radiation flipping bits? And how do you cool things in a vacuum?
Oh, yeah. The fixes are highly engineered. For radiation, they're leaning on software resilience. Systems like RedNet, which are basically designed to expect corruption and just catch the exception.
So you just assume bits will flip and you code around it?
You do. And for thermal management.
Yeah. How do you cool a GPU in space?
You get really creative with thermodynamics. They use things like loop heat pipes and phase change materials, PCMs, that absorb heat as they change state. It provides a cooling buffer.
So if we pull all this together, what's the big takeaway? It feels like we're moving from a model of just passive collection.
Right, the passive observer.
To a model of active generation where the satellite is actually computing truth.
That's it. And that shift changes the core question the whole industry is asking. We need to stop asking, how much raw data can we download?
And start asking,
How much can we infer? I mean, you have to realize orbit is just another availability zone now, a very specialized one, sure, but with amazing uptime. So think about what that means for how you deploy your next global system.